Okay. So now when I go to the class site in Canvas, I see that there's a few submissions for homework that I'm supposed to grade now. And it's like, oh yeah, I have to do that. Um, this is the only class where I have to manually grade things because everything else is like something lower level that's on my labs or whatever. But at least there's only 4 of you, so that helps. Okay, now, so I have a few items more to cover about polynomial interpolation, or specifically Lagrange interpolation, and we are going to continue this topic next week, but just laying down some basics here. Okay, so do the old screen share. Okay. Now, what I'm going to be doing, I guess it'll be a similar routine every week, is as I type these notes, since I'm basically going with a topic per week, for each Wednesday class, I'm just going to take Monday's notes and add on to them. So really, afterwards, after a week is over, Wednesday's notes are the only ones you need to look at, just to try to have everything in one place. And this also helps with doing a very quick recap so the problem we're solving here, that we want to find a polynomial that passes through given points, and I just realized I have a typo here. Ugh. Okay. I goes from 0, 1, 2 up to n, not xn. What was I thinking? Okay. And what we arrived at was, or 2 methods for coming up with this polynomial that fits these points. The first being solving a system of linear equations for the coefficients in power form, the usual form for running a polynomial, but that is not really the best way to go, as I discussed, due to lack of efficiency and robustness. And then the other way is Lagrange polynomials. So we form these polynomials that are equal to 0 at all of the x values except for one of them, where they're equal to 1. And okay, another little mistake here. I'd changed my notation midstream. Okay, so these are Lagrange polynomials where first subscript indicates the degree, and the second subscript is an index of which x value are equal to 1 at. So in fact, I'll just include that here with the formula. Okay. All right, so these are equal to 1 at x equal to xj, and are equal to 0 if x equal to xi, where I is not equal to j. All right, so so now we have this form, the Lagrange form. Pn of x in Lagrange form here, very different from power form. Okay. Okay. All right. So now what we'll talk about is good reasons for using Lagrange interpolation or not. So we dispensed with a previous method using a van der Waals matrix for very good reasons, but it's not necessarily all roses with Lagrange polynomials either. All right, so on the plus side, they're much more efficient than solving a system involving the van der Waals matrix that I described last time. So it takes on the order of, dang it, n squared arithmetic operations versus order n cubed using a van der Waals matrix. It should be solving a van der Waals system. Okay. So we gain an order of magnitude of efficiency there. Another advantage it's very easy to write down a formula for Pn of x. And the reason for that is the coefficients of Lagrange polynomials in Pn of x are just y values. That's one thing that helps. So you have a set of x values, a set of y values, and you can just rattle this off. Just write it down really quick. All right. So what are some advantages? Now, so what are some disadvantages? One is that okay. Suppose you change the interpolation points. Like maybe you delete some or you add some. Then your Lagrange polynomials change completely. So you have to totally reconstruct them to get the new polynomial. Now, I want to give a contrast here. Another form of interpolation, Newton interpolation, easily adapts to such changes. So, for example, Newton interpolation, if I decide I want to add another interpolation point, I can keep a polynomial I had before. I can just add something onto it. Now, Newton interpolation, that's covered in section 7.3 in the book. Now, I'm actually not going to be covering that in this class simply because there are other topics I want to get to, but I did want to at least mention that it's out there. Now, the thing is, all of these techniques, van der Waals matrix, Lagrange interpolation, Newton interpolation, the polynomial they produce is the same. But because interpolating polynomial is unique, which is one of the homework problems. But it may be in a different form, and there's other aspects to each method to take into account. Lagrange interpolation Okay. Another advantage, which actually relates to disadvantage, it's a good foundational ingredient for numerical methods for other problems, which is something we'll see when we get to chapter 9. That methods for approximating derivatives or integrals that rely on an interpolating polynomial, because you figure, okay, you approximate your integrand or whatever function you're differentiating by a polynomial, and then you work on the polynomial and solve a problem exactly. To do that, it's easier to work with a Lagrange form than other forms, including Newton. Okay, but this is one drawback of Lagrange I want to mention, that they don't adapt very well to change in where you interpolate. All right, and another disadvantage, which I'll spend more time on, evaluation of a Lagrange polynomial is inefficient compared to other methods. Okay. Right. Other interpolation methods. Now, to get an idea why, if you look at like these Lagrange polynomials, the way they're written out here, to evaluate each one of them, you had to perform all these subtractions. And these in the numerator, you'd have to do every single time you plug in a different x. So you're doing all these subtractions, you're multiplying all these together. So what ends up happening is, so to be more specific about how inefficient this is, it takes order n squared operations, because to evaluate even one of these Lagrange polynomials at a certain x, it takes order n operations. There's n subtractions, there's n minus 1 multiplications. These you can do once up front, but these you got to repeat. And that's for one Lagrange polynomial. Then you got to do that for all of them. That adds up to order n squared work total. Now, for perspective, order n is possible, and I will show you how that is accomplished in a little bit. Now, actually, that's what I'm going to do right now. All right, how to evaluate a polynomial efficiently. Now, I'll go back to the simplest form of a polynomial to show you, power form. Okay. Now, polynomial evaluation is something that you tend to take for granted when you're working out problems on paper all the time. And even if you're being assisted by a calculator, like, okay, you just raise x to whatever powers and so forth. It's something you don't really think about. But what if you have polynomials of high degree and a computer's doing the work? Here we have n plus 1 coefficients, and you're raising x to n different powers. So that gives you an idea as to how much work at a minimum must be done to obtain the value of Pn of x. But we want to make this as efficient as possible when a computer is doing all the work, because computers are always performing a zillion operations. So we want it to be, we want to be making the best use of those resources. Okay, so I'm going to put this on a new page. So how can we evaluate this efficiently? Use what is called Horner's method. And all I do is rewrite Pn in doing some factoring. Now, how that's done is, if I start with A0 like before, and then if I look at all the other terms, we have a common factor, x. So I'll factor out an x. So then I have A1 plus, and then if I forget about the first two terms now and see what's left, here we have a common factor of at least x squared. But I've already factored out an x. Well, I can factor out another x. And so on. Until, I want to make sure my parentheses are balanced. Okay. So ultimately, I have just, I'll have an x out here. Whoops. Okay. Okay, plus x, and then I'll have just a n. And that's where it ends. Okay, so there's this nested factorization going in here. So here's what I can do. I start with an multiplied by x. And then I add a coefficient. Multiply that by x. So whatever I have, I keep building up this expression. And what am I doing? I'm multiplying by x, adding a coefficient, multiplying the result by x, adding the next coefficient, multiplying that by x. And I keep going until I get to the outermost coefficient, and then I'm done. So the total amount of work involved is going to be n multiplications and n additions, where n is the degree. Now, to formalize this, here's the algorithm. All right. So what I'll do is I'm going to set my y value equal to an. So that'll be the coefficient of highest degree. And then I have a loop. So I start with n minus 1, n minus 2, all the way down to 0. So I'm counting backwards. Okay. And what I do then is I update. So y is equal to x times y plus the next coefficient. So that's what's happening here. I start with an. Well, I'll show you an example of degree 2. A2 is my starting point. What do? I multiply that by x, add a 1. Then next time around, I take that value that I got for y, multiply it by x, add a 0. And in that case, I'll be done because it's only degree 2. But that's it. That's the whole algorithm. So then the value I'm looking for, Pn of x, is just equal to y. And this is how you can see each one of these steps takes one multiplication, one addition. We're going from n minus 1 down to 0. That's n total iterations. That's how you can see there's n multiplications and additions. So that's how you can efficiently evaluate a polynomial that's given to you in power form, at least. Questions about this Horner's method? And no, I was certainly not expecting to start using Horner methods when working with polynomials on paper. But if you're going to make a computer do the work, it better use this. Now, so this is something that's useful for a polynomial written in power form. But Lagrange form is that sort of approach that Lagrange form lends itself to. There's no simple way to do this kind of nested factorization with a polynomial written in Lagrange form as opposed to power form. The Newton form, and I know I'm not covering Newton form, but I just want to mention that Newton form, while very different from power form, is close enough to it that a nested multiplication approach, something like Horner's method, is possible. So that kind of polynomial written in power form or Newton form can be evaluated using a relatively small number of operations, whereas Lagrange form it's not available to that. But we are not out of luck with Lagrange form. All right. Now, one thing that's kind of nice about numerical analysis is that all fields of math are constantly changing, but a lot of those changes most people would not see. Like, it might only be known to experts in that field. One thing that's kind of annoying that you've come across, no doubt, is that like say calculus textbooks. Calculus textbooks are always coming out with new editions every so often, and you might think, "Wow, is calculus changing so often that that this is necessary?" And well, the answer is no. Calculus has not changed in any meaningful way in over 100 years. Now, textbook publishers will argue that methods of teaching it are changing, and I imagine there's some truth to that. But I don't know if the kind of change that necessitates nearly identical new textbooks every couple of years. And of course, now I'm thinking of the textbook you're using for this class. I will have to put out new editions every so often, but not that often because I don't have that kind of energy. So for the most part, these areas of math, in terms of what's used by, I guess, general population, is fairly static. And I'm reminded of what some of my students would ask me, undergrads. They'd say, like, how can you be doing research in math? Isn't math done? And you can't fault them for thinking that way, because the math that they see in most majors, you could argue, is done. It's just that the higher level stuff isn't. But numerical analysis is a relatively young field. It has been in existence for over 100 years. But it's really once we had electronic computers that things really took off. And that, that was, yes, it was a long time ago, but compared to other areas of math, it's almost in its infancy by comparison. So this technique I'm going to show you, called Barycentric interpolation, which is a more efficient way to evaluate Lagrange form. That should be Lagrange form, not norm. We'll talk about norms another time. This is a very recent development, 2004. In fact, when I pitched my textbook to the publisher, so I wrote a proposal and they sent it out to people in my field to evaluate it. And one of them pointed out that, I didn't have barycentric interpolation in there, so that makes the textbook seem kind of dated. And the thing is, I honestly wasn't aware of it at the time because it was that new. So I included it. So what is barycentric interpolation anyway? So we work with the Lagrange form of the interpolating polynomial. And it's a rather strange way to go, but it's quite cool. All right. So first, I need to define some notation. I need to define this polynomial, pi n of x, to be equal to the product of all these linear factors, x minus each of the x values. So then pi n of x has degree n plus 1. What's also worth noticing is that this looks a whole lot like the numerators to the Lagrange polynomials that we see here. Did anyone tell me what's the difference, though? What's the difference between these numerators of Lagrange polynomials compared to this polynomial here? Might help you to answer to look, well, how do these two differ? Again, just the numerators.
This one's x minus.
Dang audio.
Sorry. This one starts with x minus x naught.
There's that lovely echo. But I believe I get what you're trying to say. Or, well, you're not trying to say it. You are saying it. We're just trying to get it through to me. So, yeah, these start differently because this one leaves out x minus x naught. What does this one leave out?
X minus 1.
Yeah. So each one of these Lagrange polynomials leaves out one of these linear factors. Whereas to be degree n, this has all of them, degree n plus 1. But what that means is it gives me a way to write the Lagrange polynomial as follows. I can write it as pi n of x, but then I can divide it by x minus xj. And then I still have down below a product. I goes from 0 to n, and then I not equal to j of xj minus xi. And I have to be more careful how I write this. I'm going to take this factor here And I'm going to put it to the left. Okay, because it's not to be included in this product here. All right. Now, now here's an interesting fun fact for you. I can actually simplify this. Okay, so I have pi n of x up top. I have x minus xj down below. And then this product here is actually equal to pi n prime evaluated at xj. Now, to see this, if I were to take a derivative of this, first of all, big mess. You got to use a product rule, and you have n plus 1 factors, so your product rule will have n plus 1 terms. In each term, you take a derivative of one of these factors, which is 1, so that's nice. But then, when you plug in x equal xj, then when you have a product of these factors, most will go to 0 because one of these points will be xj. The only exception will be if x minus xj is the one that is differentiated, it goes to 1. So then you have a product of all of these for I not equal to j. All right, so actually, I know that was a mouthful to digest. But to help, I will write out the derivative. Okay. So a sum stemming from the product rule, and then each one of these all right, so the product rule gives you this. If I plug in xj, then if x minus xj appears in here, the whole product will go to 0. All of them will go to 0 except one. And that's where the index here equals whatever I plug in here. Okay, so that's why this product, you can see this is very similar to this, is equal to pi n prime at xj. All right, so this gives me another form of the Lagrange polynomial that's actually easier to work with. So now I'll write out Pn of x. So that is equal to, and I'm using what I had before. This formula right here. So I have yj, and then my Lagrange polynomial. But now I'll fill in what this is. All right, so I'll have up top, I'll have yj pi n of x over x minus xj pi n prime of xj. Okay. Now, Did anyone tell me? I don't know if it really makes a simplification, but okay. What algebraic manipulation can I do on this? To at least make what I'm summing up simpler. I know it's a big question, but we'll be careful not to give it away. When you have a sum over J, like I have here, anything that does not depend on J can factor out. Pi n of J is such a factor. Now, that doesn't seem to really mean anything. I guess I couldn't really call it a simplification, but it's something that is going to be very helpful to us in a little bit. Now, now what I'm going to do is suppose my function I'm interpolating is just a function that's equal to 1 everywhere. I can write it the same way. So all I have to do is set my y values equal to 1. Because this is going to be exact. This will be exactly 1 at every x. Why? Because 1 is a polynomial of degree 0. Here I'm interpolating it by a polynomial of degree n, which will certainly be exact for a polynomial of degree 0 or any other lower degree polynomial. Now, here's the kicker. Since I have Pn of x over 1, I can divide these. And what glorious thing happens there? That really does make things simpler. So here I'm dividing the left sides of these equations, therefore dividing the right sides. What simplifies? trying to move it over so that they're right on top of each other. So now it'll be easier to see that way. So if you divide these,
the numerator denominator cancel.
There is a cancellation. I'm not sure if you have the right one, but I need some clarity there.
Like when you.
I'm sorry, what?
When you divide it, couldn't you flip the fraction? So it would, I guess, would it just be y sub j?
No, because the thing is, we have a sum of fractions here, and we
Yeah.
have some fractions in the yeah. But there is something that does cancel. What is it? Really, so many pieces to consider. Someone take a stab at it. So all I'm doing is I'm just taking this divided by this. Yes, these cancel. So now we take a look at what's left. So up top we'll have this summation. And down below, we'll have this one. What happened? That was weird. Okay. Well, okay. Okay, let's try it again. This really shouldn't make a whole fraction disappear. Okay. Oh, I see. I forgot a brace. Okay, and I need to make those a little bigger. I don't like how when you put stuff in a fraction like this, that it makes it so tiny. But fortunately, there is a way to deal with it. Okay, so now we have it. All right, so this is a more efficient way to evaluate the Lagrange form. So you just evaluate these sums, and each one of these sums takes requires order n operations. After computing what are called the Barycentric weights, which are really defined to be 1 over pi n prime. So I'll call these wj is equal to 1 over pi n prime of xj. All right, so that's what these are referred to, barycentric weights. So once I have those, now these take a little more work to evaluate, but you only have to do it once up front. So I'm going to rewrite this formula in terms of those. Okay. Oh, I didn't need that other fraction. Okay. So I could call this yj times wj, and then I don't need this down below. And the same thing in the denominator, we'll have just the weight. And get rid of this. Okay, so there you have it. So now we have a nice, efficient way of evaluating a polynomial interpolation, or interpolating polynomial. Now, can anyone tell me, when is this formula not useful? When does something go wrong?
When the bottom is 0.
Yeah. So if either denominator is 0, like here we have, what if x is equal to xj for any j, then we have a problem here. But how come that's not really a deal breaker? Because if I plug in x equal to xj in here, so that's really what I'm trying to get. Well, what should the value be? The xj is one of our interpolation points. So if I set x equal to xj, I actually already know what the result is supposed to be. What is it? What conditions is Pn of x supposed to satisfy in the first place? Think about why we define the interpolating polynomial. It's a y value, corresponding y value. So you plug in, because the x's, our data is xj, yj. Those are our interpolation points. So we plug in xj, yj is supposed to come out. Does everybody see that? And not from this formula, but if you do plug in x equal to xj, you just know the answer is supposed to be yj. Therefore, you would not use this. So it's not really a big deal, but you can't at these points because you know what you're supposed to get anyway. All right, questions about Barycentric? Okay. Oh. Something went wrong here. Oh. Someone took over control. Okay.
My cat took over control.
Okay. All right, so let me take control back. That was kind of freaky. I thought I'd clicked on something wrong. Okay. When I had cats, they would chew up homework I was supposed to grade. So they always have their way of helping with the educational process. Okay. Now, one more thing I'd like to show you is if we're using a Pn of x to approximate some function, so in other words, our y values are given by some specific function f of x, then how accurately does Pn of x approximate f of x when x is not equal to any of the interpolation points? Because if x is equal to one of these, Pn of x and f of x will agree, and Pn is literally designed that way to agree at those points. What about elsewhere? Now, we know that in some cases it's not a good approximation. Like one example I showed you, 1 over 1 plus x squared, how the error was awful at the boundaries. So we'd like to get a handle on that. So we need a formula as much as possible for the error to be able to estimate it for a given f of x, a given interpolation points. So I'm going to come up with the error formula. And I could just state it, but it's more fun to prove it to an audience of mathematics graduate students. And I find the approach to proving its formula to be quite unorthodox and honestly rather elegant. But definitely not the sort of thing that one would come up with out of thin air. Okay. So I have this function I'm going to define. I'll call it phi of t. So that is equal to f of t minus p n of t minus, and then I'll have in this fraction upstairs I'll have p f of x minus p n of x, and then down below I'm going to have pi n of x. So this is the same pi n as before. Then I'll have pi n of t out here. So pi n is still the product of all those linear factors, x minus x naught, x minus x1, etc. Okay. Then, so in this function, this is a function of t. And x is thought of as a constant. And not equal to any of the interpolation points. Because if it were, we'd be dividing by 0. Okay. T is a variable. Then, what happens if I plug in any of these interpolation points? Because remember, f and Pn are supposed to agree at these points. So if I plug in t equal to xi, did anyone tell me what this will turn out to be in that case? Like, what would this part be? Just that part.
F of I minus P and
It is, but what would that turn out to be? Keeping in mind how keep in mind Pn's purpose. Pn's purpose is to agree with f at selected points.
maybe 0.
Yeah, this would be 0 because if f of xi minus Pn of xi, Pn, which is yi, both of them are equal to yi. So that part goes away. This part is some constant. That depends on x, not t. What about this? If I plug in t equal xi here, what will that be? And I'll return to the definition. Here's a definition. So if I plug in one of the xi's into here, what will I get? If I plug in x0 or x1 or anything, any indexed x in that range.
It'll also zero out.
Yeah, because one of these linear factors will be 0. So the whole thing is 0. Okay. Now, what if instead I plug in t equal to x? So if I set t equal to this x right here, what will I get in that case? Yes, the audio kind of garbled there, but I believe you also said they also be 0. Yeah, because here I have pi n of x over pi n of x. These cancel. So then this will additively cancel with this, leaving us 0. Therefore, phi of t has n plus 2 distinct zeros. Now, I know they're distinct because all of the xi's are assumed to be distinct, and x is assumed to not be equal to any of them. So we have n plus 2 distinct zeros altogether. Now, I'm going to recall a theorem for you from Cal 1. Rolle's theorem. If Rolle's theorem says that if f of a equals f of b, so if f is equal at 2 points, then f prime is equal to 0 at some point in between. Now, I can apply that theorem repeatedly with this function phi. Phi has n plus 2 zeros. Therefore, phi prime has n plus 1 distinct zeros that lie in between the n plus 2 zeros zeros of phi of t. Well, if phi has n plus 2 zeros, phi prime has n plus 1 zeros, so it's one less. I can keep going. I can keep taking more and more derivatives of phi and knowing that they have a certain number of distinct zeros. So we keep going all the way to its extreme. So the n plus first derivative, I need to put that superscript in parentheses. So you may be familiar with this notation. With a higher order derivative, instead of using a bunch of primes, I have an n plus 1 in parentheses as a superscript. So that's n plus first derivative. So this derivative has a 0. I'll just call xi, or the Greek letter squiggly. Now, question is, what is the n plus first derivative of all this with respect to t? Well, let's get that worked out. So phi n plus first derivative of t is equal to, well, first we'll have just the n plus first derivative of f. Okay. Now, keep in mind that Pn is a polynomial of degree n. So what is its n plus first derivative? Like you have a quadratic and you take a third derivative. What do you get?
Nothing.
Yeah, 0. All right. So we get nothing from here. This fraction is not a function of t. It's a function of x, which is a constant. So this part we'll just keep as a constant factor. So let me just copy that. Okay, so we'll put that here. And then what's left is this, the n plus first derivative of pi n of t. It will not be 0 because pi n of t is degree n plus 1. And we're taking the n plus first derivative. Now, can anyone tell me what type of function that would be? So if I have a polynomial of degree n plus 1, and I take the n plus first derivative, so the number of derivatives is equal to the degree. So again, back to the previous example, you have a quadratic, you take a second derivative. What kind of function, what kind of function do you get?
A constant.
Yes, it's a constant. Now, look this way. If I took pi n of x here, and I multiplied it out, and then took n plus 1 derivatives. Well, if I multiply this out, the only term that matters for this is a term of degree n plus 1. That comes from multiplying together all these x's. I would get x to the n plus 1 plus all these other terms that I don't care about. So if I take x to the n plus 1 and I keep differentiating it, I keep pulling down exponents, I keep applying a power rule. So that would give you a factorial. So I'll fill that in here. So the n plus first derivative. All right, so if you have a polynomial that's monic, its leading coefficient is 1, and you take a derivative equal to the degree, it's that factorial. So that's one of those good to know things. All right. So that's what I get for the n plus first derivative. But this is 0 at a certain point. So if I plug in t equal to squiggly, so I can set t equal to that in here, and this is 0, I can rearrange this now. And I'm going to solve for this. That's what I want. That's the error. So f of x minus p n of x is equal to, so think of all this being set to 0, and then you're rearranging. So what you get is, okay, you get n plus first derivative, evaluated at this point squiggly, over n plus 1 factorial, times pi n of x, which is, I was working the definition, x minus x naught, minus x1, and so on. Okay. So this is the error in the interpolating polynomial. Now, this point, C, or squiggly, we don't know what this is. Well, okay, there's one thing we do know about it. It is unknown, but it lies in an interval containing x naught, x1, up to xn. Okay. Oh, and also x. Why? Because we started with all these points, x and the xi's. Those are where phi is equal to 0. So this mysterious point, the 0 of the n plus first derivative, must lie in between all of these roots. So we know that much, but that's it. Okay, so this is labeled the error in the interpolating polynomial. All right. So, and as we see in some examples, this error can get large. But there is something that can be done to try to at least somewhat make it smaller. And that's what I'll get into next week. Okay. So questions about any of this? Or the homework, for that matter. Since we have a few minutes. I can't hear you, Walker.
I'm on mute. I'm still echoing. But I said, while I've got you here, I know we've been talking about the first homework problem.
Yeah.
And I know I know I'm off target. But I know what it means for a matrix to be invertible. But I'm kind of confused on how to necessarily tie that in there.
Okay. Thing to keep in mind is not just what it means for a matrix to be invertible, but what are the ramifications of a matrix being invertible for a system of equations involving that matrix? Like when it comes to existence and uniqueness of solutions, that's why, like in any linear algebra class, there's always, because things work out so nicely in linear algebra, it's always a situation where you have, well, the following statements are all equivalent. Like, okay, if A is invertible, then what does that mean? And I know it's something you would have encountered in such a class, and you've probably had plenty of time to forget it by now. But for example, if A is invertible, then the system of equations AX equals B has a unique solution, no matter what B is. If things like that, that come into play here.
Okay.
And actually, yeah, in fact, that was something I mentioned last time when talking about the van der Waals matrix. How so one way in which we know that the interpolating polynomial is unique is that is because the van der Waals system is invertible. Now, I should say that the problem that I assigned is meant to explore a different approach. And I don't know if I made that clear enough in the problem statements, which I don't remember because I don't have a book handy here. Okay. I have in front of me the problem statement from a message you sent. Okay. Because another way to look at it, besides the matrix, I know that's one approach, but it's just properties of polynomials of degree n. When it comes to their when it comes to their roots, because and I remember telling you this earlier that a standard approach to uniqueness proof is assume there are two solutions, look at their difference, show the difference must be 0, and if you think of that in terms of like if you look at the difference Pn minus Qn, what do you know about it as a polynomial of degree n? That would lead you to conclude that it must be the 0 polynomial. And okay, sorry, I know I've run a little bit past time. So Chelsea, I know you have class, so feel free to skedaddle. But I'll stop recording here so that well, actually, okay. Actually, I'll keep recording as long as anyone's here, so that you don't miss anything. Okay, but I guess I can continue sticking around for any questions anybody has. But okay, not sure what's going on there, but okay. Are you talking, Walker? Because I can't hear you.
I forgot. I'm using it was interfering with the sound earlier.
Okay. All right.
Mm-hmm.
Okay. Well, all right. So I'll just stick around just for questions. Yes, Chelsea, don't be late to your class. But I'll keep recording in case something pertinent comes up. Okay. All right. Okay. Oh, and Taylor's still here too. Good. All right. So that like in terms of how polynomial roots relate to their degree, things like that. Because one thing I realized just now talking about this problem was like I know the work you were showing me was still dealing with the matrix, and then I realized you know what, I shouldn't have had you down that path just because that's too similar to what was already discussed in the text, and the idea here was to look at a different approach. So,
Okay.
yeah.
So I'm trying to think of the polynomial roots in relation to the degree.
Yeah, like yeah. So for instance, if you have polynomial of degree n, how many roots is it allowed to have?
Like a polynomial of degree 2 would have 2 roots, so n roots.
Yeah, and cannot have more than that. So for now in this case you have this. So Pn and Qn are both degree n. So certainly their difference would be. Given what, so from what's given about them, what can you say about the root of this difference, Pn minus Qn? So that's what I want you to think about.
Okay. They're both degree n.
Yeah.
So they have the same amount of roots.
Yes, but now focus on the difference. So think of a new polynomial. We'll call it Rn. Is Pn minus Qn. And because both Pn and Qn equal yi at these x values, so this is about the roots of this difference that I'm calling R.
The difference, the roots is 0.
Sorry, I'm not sure if that came out right, but
Sorry, you said to think of just focus on the roots.
yeah, the roots of the difference.
The roots of the difference is 0. Or the difference of the roots, sorry.
Okay. Well, okay. I think things have troubled here, but yeah. So all right. So at these x values, yeah, but the difference would be 0. So I think so. What you're really getting at is that each of the x values is a root.
Okay.
Because the difference is 0 at those points. So I want you to try to take it from there.
Okay, so the x values is a root because the difference is 0 at both points.
Yes.
Or all points, or
all of those xi's.
yeah.
Yeah. So because it's equal to 0 at the given points, the x0, x1 up to xn. It's equal to 0 at those points, and you want to use what you know about polynomial roots to conclude that therefore this difference must actually be 0 everywhere.
Okay.
Okay. So,
Okay.
are there any other homework questions?
That's all I have.
What?
You probably know that's all I have. So.
Okay. All right.
Thank you.
Okay. All right. Nobody else? Okay. All right. Then I guess y'all can scrape. Although, Taylor, I do want to talk to you for a quick sec if possible.
Okay.
I'm going to stop the recording here.